Okay, what about what we have seen last week, very quickly? I introduced one model, which is called this GNP model. It's made of n vertices, and then you have a probability P of having an edge between two vertices, and this probability is independent of what happens for all the other edges. So all edges are independent. And we can compute everything in this model, in particular, the probability that a certain graph has m edges. There is a formula, and it's, in fact, a binomial distribution. We can also compute the expectation of the degree. But it turns out that the expectation of the degree is n-1 times p, which means if n is big, this becomes a huge number, which is usually not useful. So what we do, we in fact renormalize p. We define p as c over n-1. And then we can see this c is just a constant, but it means the expectation of the degree is going to be c. And we can then take even the limit when n goes to infinity of this and find out that the expectation, the limit when n goes to infinity of the expectation of the degree equal to k is given by the Poisson distribution. So it's a limiting case of the binomial distribution. Then still in this framework with this renormalization, we can look at the giant component. Remember, the giant component is a connected part of the graph which has a size which is growing. So we grow different graphs, but the size is bigger than epsilon times this gn. Epsilon is fixed independently of n. This is important. And this happens, we have shown if c is bigger than 1, and we can even find the probability to belong to the giant component. It's a solution of this equation. We can also study the small components, because besides the giant one, we have small one. It turned out that with the probability 1, these small components are trees, and we can even have precise distribution of these small components. So we can really study everything. There is one more coefficient which I introduced. It's called the clustering coefficient. You can either define it globally or locally, and the idea is look at the number of triangles divided by the number of such things. Maybe I haven't been precise enough. It means here you can either have an edge or not. It doesn't mean, well, I draw this last week. It doesn't mean that you have no edge. You either have one or not, because otherwise you might have something which is bigger than 1. So it's really the number of closed triangles divided by the number of things which look like this, but no matter what happens on the third edge. And it turns out that for this GNP model, we can check that it's equal to P. Weaknesses of this model, or at least what happened, is that the clustering coefficient is very small, which is sometimes annoying. And also the degree distribution, this Poisson distribution has an exponential decay. And for many applications, this is decaying too fast. We would prefer 1 over a polynomial. So today we introduce another model, and I already mentioned this. And if you're interested in oral exam, please contact me as soon as possible, because it's better if we organize this before your exam. And most probably there will be only one more lecture, so next week. So don't miss it. And also you will have there will be a picture. So today we'll learn what is called the configuration model, which is still a model of random graphs, but with a different starting point. In particular, we want to fix the degree distribution. So the first section is how we build this model to construction. So there are two equivalent approaches. We will clearly see that they are equivalent. So I start with the first one, and then the second one will be quite easy. We fix a n, which is going to be the number of vertices, and we also fix a sequence that I call ki, I between 1 and n. And ki is a number also in n. And what this ki is going to be, it's going to be the degree of vertex xi. But I need just one small assumption, is that the sum of ki has to be an even number. You can already, okay, we will see why very quickly. So I impose that the sum of ki is even. And I call this even number 2m, because m is going to be the number of edges. So this ki, I from 1 up to n is called NM sequence. It's a sequence of n numbers, all integers, summing up to 2m. Okay. Then whenever I have such an NM sequence, I can set nk. It's going to be the number of I in 1 up to n, so that ki is equal to k. So in my collection of numbers, I count how many times I have the number 3 or the number 5. And nk or n3 is the number of times I have 3 in this collection of numbers. Okay? And clearly, what is the sum of nk? K? Can you tell me what number I should get? No, not n. I should get just n, because I have 3 times the number 1, 2 times the number 3, and so on. And I end up to list all possible solution for k, for ki. So this is the sum of nk is n. And what is the sum of nk times k? I sum up over k. Now just another number that I haven't used. It's 2m. You know, I had this collection, maybe I just take an example. Let's say we have the collection 1, 3, 2, 3, 4, 1, 5, doesn't matter. I count nk give me how many, n3 give me how many 3 I have in this list. Then the sum of 3 times the number of 3 plus all the other one give me exactly the sum of all these numbers. So these two relations are quite clear. Okay. And I define one more thing. I also set pk, which is going to be nk divided by n, and it represents the probability of, the distribution. It's a probability distribution. So I should say the family pk is the probability distribution of what is going to be the degrees. I haven't introduced the degrees. Oh yeah, I mentioned this going to be the degrees. So this is a probability distribution of the degree. And indeed, just check indeed, what is the sum of pk? It's nk divided by n. We know that the sum of nk is n. So the sum of pk is 1, right? So this is the first approach. We start with a family of ki, I going from 1 up to n, and we define this probability distribution. And the second equivalent approach is start. We start with a number n and with a distribution pk. And then I reconstruct the other thing. Then we set n times pk. It's going to be nk. If n is the number of vertices, no, the number of edges, total number of edges, and pk is a probability. No, n is a number of, correct, it should be correct. Yeah, I just, now if I start, I reconstruct nk by this n times pk, so I get nk, and we can get an nm sequence. How do we get an nm sequence? So we get an nm sequence by setting. So I do the sequence 0, 0, 0, 0, then 1, 1, 1, 2, 2, 2, up to a certain number. And how many 0 we have? We have n0. How many 1? We have n1, 1. And how many 2? We have n2. And these approaches are essentially equivalent. The only thing is, I'm not completely sure that this number is going to be an integer. It depends on your distribution. But you suppose that this is, you manage to have a distribution such that this is an integer. It's not always the case. It depends on your pk. It might not be the case, but you can arrange this. So what is the idea? So this is the two equivalent things. And now what is the construction? So keep in mind, either we start with a certain family ki with I from 1 to n, which is going to be the degree, and we end up with a probability distribution, or we start with a probability distribution and we construct this sequence. But then what do we do with it? We just construct the graph. So now, given nm sequence and n vertices, which I call x1 up to xn, we are going to assign ki half edge. I haven't introduced the notion of half edge, but what is a half edge? It's a half edge. And now, let's say we have x1, x2, x3, and I suppose that k1 is 2, k2 is 3, and k3, so k3 is 3, k2 is 2, k1, no, it was 3. K1 is 2. So we assign K1 half edge. And this is also called a stub. So it's a half edge, like this. So at each vertex, we assign these half edge. And now randomly, we connect them. So randomly, I start with one. I do it like this. This one, oh, like this one like this, and this one like this. Then, so we assign Ki half edge or stubs at Xi and connect these half edge randomly and connect the stubs at random. And now you can see in this picture why the sum of these degree should end up to an even integer. Because if I have an odd number of half edges, then I would have a pole-only guy. So I need to close all edges. So I need to have an even number of half edge.
Allowed to have 0, like destroying that?
Yes, and it was visible here. It's also possible that x4 as k4 is equal to 0. Yes, it is possible. Nobody is connected to this point. Yes. And as you can see, I did it on purpose. We can have loop, and we can also have multiple edge. If they are connected at random, there is no reason why we have no loop and no multiple edge. So, and if ki is 0, indeed, we don't connect this point to anybody. And now you can easily understand the difference between the two approaches. Either you start with this collection of numbers, or you say we have 30% of vertices which have 3, 20% which have 2, and 50% which have something, and you do the same kind of graph, right? So it's a different approach compared to the model of last week. What is the advantage? What is a specific feature? Is that we fix the degree distribution from the beginning. So first, there are several remarks. Indeed, Ki is equal to 0 is allowed, which means isolated vertex are possible. This is the first one. Second, okay, this, if I forget this point, the graph is connected, but it could be disconnected with this. By choosing it at random, I could have different possibilities. So the graph can be disconnected. There is no reason why it shouldn't. 3 loops and multiple edge. Can occur or can take place. And 4, which I mentioned, the degree distribution. The degree distribution is fixed a priori. So you started with this degree distribution. It's not like the previous model when we observed that it's a binomial distribution. Here, you decide. So it's given a priori. I hope you like this word. It's a nice word. I think it's Latin. It's even older than French. And that's why in many books, they even put it in italic because, because of its origin. It means it's given even before. One more remark, maybe 5. If you choose the pk, the collection of pk, according to binomial distribution, are you back to the previous model, to binomial distribution? Because this is the distribution we had before. In the last week, we had the binomial distribution. So if I choose the pk following the binomial distribution, are we going back to the GN model, GNP model? Can you answer yes or no? Okay, one no, somebody else? Indeed, it's no, but why? No, no. Because in the previous model, we didn't allow loops and we didn't allow multiple edges. So even if we choose this pk according to binomial distribution, we are not in the GNP model because loops and multiple edges can take place. While in the GNP model, they were not allowed. So it's not the same, even if you choose a binomial distribution. Okay. Right, but now we can again do many computations with this. And so I'm going to study, I will provide some results, and then we will see why this model is interesting or what's interesting. So some results. The first one is given xi different from xj. So if I take 2 different vertices, the probability of having an edge between them is given by. So this is the probability of the edge xi, xj. Probability of having such an edge. Let me give you the result. Today, it's quite a lot of computation. If you are familiar with probability and with combinatoric, some result will be easy. Otherwise, it's less familiar. So why we have this number? Remember, the total number of edges is 2m, right? So if you start at xi, and we want to have an edge, we have altogether 2m possibilities, but it will depend. This number will depend on how many half edge you have here, and how many half edge you have at xk. And so the number of, if you start here, the number of stubs around is 2m minus 1 because you start with 1. So this minus 1 is the one you start with. But now you have also this factor ki because you have ki possible stub here, and you have kj possible stub here. So this gives you the probability of having an edge between xi and xj. And what is the probability of having a loop at xi? So the probability of an edge xi, I choose the same. It's again 1 over 2m minus 1. For the same reason, when you start at 1, you have this number of possible stubs. And you have the factor ki times ki minus 1 over 2, which is how many possibilities you can find, how many options you have to take 2 stubs around xi. Yeah, it's 2 stubs at xi. Okay, so let's keep these 2 quantities in mind: the probability of having one edge between xi and xj, and the one of having one loop at xi. And of course, yeah, that's it. I still set some notations with the definition 1 over n times sum of ki. I define this, what is this quantity? You can directly observe that this is nothing but the expected degree. But let's do a small computation because it will be useful. I can rewrite it as 1 over n sum of nk times k. And I sum now over k. Why? Because this is what I said before. You have ki. For example, you will see 3 times the number 4. So you are going to write 3 times number 4. So you do this sum nk, but now what is nk divided by n? It is the sum of k of pk times k, because nk over n is pk, and this is nothing but the expectation of deg of x. You think about the distribution. If this gives you the distribution of degree, then when you do this, it's exactly this quantity. And another notation which I define, which is 1 over n sum of ki squared to sum over I. I let you do the same computation, and you find that it gives you the expectation of the degree of x, but now square. And this is true for any x, for any vertex x. These are just notations, but they will appear. On the left-hand side is shorter than the right-hand side. These are they are also the first and the second moment of the distribution of degree. So the first moment, the mean is the first moment of the degree distribution. This is the second moment of the degree distribution. Do they always exist? We have just to think about this for a second. Be careful about one thing. Of course, if I write it like this, it means n is finite. But if I want to take a limit n going to infinity, just be aware that whenever you have a distribution, the mean or the second moment do not always exist. For example, if you take a distribution of the form So just be careful. Mean and second moment of a distribution. Do not always exist. I'll let you think about one example. If the distribution is not decaying fast enough, it's a probability distribution, so the area below the curve has to be 1. But it's like an integral. The fact that the function is integrable doesn't always mean that the function is square integrable. Yeah. Yeah, this is what I said. If you use this definition, then it means n is finite. But now if I give you pk, the distribution, and if I give you an arbitrary distribution, these two quantities do not always exist. I just wanted to emphasize it. So indeed, at a certain point, if we take a limit, n goes to infinity, or if I give you a degree distribution arbitrary, this quantity might not exist. I just wanted to recall it. But yeah, if I write this, of course, I am not allowed to divide by infinity. So I can only give this definition with finite n. But yeah, this sentence just, this is correct. If I give you a distribution, be aware that the mean or the second moment might not exist. Okay, I just make a very small parenthesis. And this is precisely what I was not happy in the book I used. I will not explain it because it's slightly more advanced, but for it's a random variable. If you know what it is, I just want to recall a certain relation. We have, and Ka, it's an indicator function. Indicator function on a set A. On a set. So it means it takes the value 1 if the point is in A, 0 outside. Then what we have? If you don't understand this remark, it's okay. It just helps to understand the next one. So if we have a random variable and an indicator function on a set, then what is the expectation of chi A of x is the same as the probability that x belongs to A. And this is the sum over G. This notation, remember, means disjoint union. So we have A, which is made of, this is A1, A2, A3, and AJ, and altogether, this is A. So this notation is for disjoint union. So what I just wanted to recall is this formula, the expectation of an indicator function on a set is the sum of probability. Again, if you're not familiar with this, it doesn't really matter. But if you understand this, it helps for the next argument. I cannot introduce random variables on everything here. So what is just my aim for the next few minutes? You remember in the first picture I did with a few stubs, we had one loop and we had also two multiple edges. So you can wonder, oh, in this model, are they generic or not? Do they take place often or not? And I'm just going to give you an argument. No, if n is large enough, these loops or multiple edge are in fact very rare. So let's just look at the argument. So I just want to emphasize that they are very rare. So the expectation for the number of loops in the graph is given by this is the expectation of, I call it L, this is loops. The expectation for the number of loops. And this is, yeah, what surprised me at the beginning, the sum of these. Oh, I didn't introduce a notation. Maybe it's better to introduce. Before I said, oh, no, I can just expectation of xi. I should have introduced something shorter. And this is a little bit surprising. The expectation of the number of loop is this, oh no, sorry, not expectation, probability. But before I introduce the probability of having a loop at xi, it turns out that the expectation is given by this sum. Which means now if I replace, it is the sum on I of what we had. We had ki minus 1, 1/2, 2m minus 1. This is what we had before. I let you check. This is with the notation I introduced before. This gives me k square minus k divided by 2a minus 1 over n. How do you get this? You know, I'm allowed to divide this by the numerator and the denominator by n. I can always do this. Then you observe we have the sum of ki square minus over n minus the sum of ki over n. It gives me exactly what is there. And 2m over n, you can check it is exactly k. And we have just this minus 1 over n, which means I can still write this as a square minus k divided by 2k 1 plus 4 of 1 over n. I hope you have all attended a good course of Calculus 1, which means if I have k minus 1 over n and is big, you can factor something and you will have a 2k times 1 plus something going like 1 over n. So it means the leading term for the number of loops is this. And what do we observe? This number is independent of n. I forget the remainder term because the remainder term goes to 0. So it means the number of loops is finite. So even if n is becoming big, the total number of loops is finite. So it means they are becoming very, very rare. Okay. Yes, there is no mistake in this computation. I'm confident about this one. Now you can do the same. Maybe I will save some time by not doing the detail. It's written in the notes. You can do the same computation for the probability of double edge. I don't say multiple edge because if you look we first do the probability of having this. If we want to do the probability of all multiple edges, I should add the probability of having 3, the probability of having 4. Of course, they are becoming less frequent. So I just write the probability, or no, the expectation. In the notes I've given the expectation, so the expected number of double edge. It's a similar computation. I just give you the answer. It's not difficult. It takes a few minutes. 1/4 times k squared minus k over k. But now square times 1 plus O of 1 over n. It's a similar argument. And again, what does it mean? This number is given. It's a certain number. So it means the expected number of double edge in your graph is finite. So if you take a bigger and bigger graph, they are becoming more and more rare. So it means that the total the expected number of either loops or double edge is finite, which means if you divide now by the number of vertices, if you want to know the density of loops, so you divide the total number of loops by n, this number is becoming very small. So it means the density of loops or double edge goes like a constant, which is a constant I have written, divided by n. If you want the density, you need to divide by the total number of vertices. This gives you the density of loops or of double edge. And of course, the same computation for triple edge or quadruple edges and so on.
So is there any structure that is more likely when you do this?
No, it means, of course. Okay, what does it mean? It means if you take n large, and this is quite natural, take n large, which means 6 in my picture. Now I draw the stubs. I have a even number. When I connect them at random, okay. I connect them at random. The number of loop, here I still have one double edge, but the number of loop or the number of multiple edge is much smaller than the number of arbitrary edge between one vertex and the other one. That's the meaning. So if you draw a big graph and you just point out the loop, you are going to find them very rarely, and the same for multiple edge or triple edge. That's the meaning. The density goes like 1 over n, so most likely you will have edges like this one. One edge between two distinct vertex. That's it. That's the meaning. All right, so even though they can appear in this model, the total number, the expected total number is finite. So if you divide by the number of vertices, you get something which goes like 1 over n. Okay. Now I want to add additional properties of these graphs. One which it's a little bit surprising when you don't think carefully about it. So additional properties. What is the idea? We have a vertex X with a certain number of half edge, and we have a Y here with a certain number of half edge. And I go from X to Y. Suppose we have an edge. So we start at X, start at vertex X, and this is important. And go to a connected vertex Y. Okay, so I start like this. What is question? What is the probability distribution? No, the probability that Y has a degree K. What is the probability that Y has a degree K? So if you don't think at all, what is the stupid answer you are going to say?
1.
No, not 1. This is very stupid. What is the probability? We have a degree distribution, which is pk. So most likely, it should be pk. So this is a trivial answer, which is not correct. Trivial answer.
Yep, 1.
pk, because among all vertices, you have a distribution of P1, P2 up to Pk, and so on. So the most likely is to have the degree K is this number Pk. You know, if you have a distribution like this, discrete, and I fix a K, then I'm mostly probably going to get Pk. This is not correct. Why?
He knows there's at least 1 edge.
This is clever. Thank you. Say it differently, I know one thing. I will never reach this guy. This guy with P0, this one which has no edge, it has there is a certain, in the distribution, okay, my picture, we have some with 0. So I cannot reach indeed this one. I can never reach this one. So for sure, I cannot find an arbitrary vertex because there are some which I will never reach by this construction. So indeed, it cannot be pk. Because, for example, I will never find p0, the one with 0, because they are not connected. So we have to be a little bit more clever in order to find the distribution of this Y. What is the only information is that this Y is indeed connected. So first, for k bigger than 0, because I will never reach an edge of degree 0. So for k bigger than 0, there exist how many stubs of attached to a vertex of degree k are available? Think about it. How many half edge are available for a vertex of degree k? So there exists n times k times, should write n times pk times k stubs belonging to vertices of degree k. Let's check. N times pk give us a number of, so pk is a probability that a vertex has k stubs. If I multiply by n, it gives me the number, it was nk, the number of vertices with k, with degree k. And if I multiply by k, it gives me indeed the number of stubs belonging to vertices of degree k. And so the probability that I touch one, the probability that I touch such a stub, was the probability of reaching one of them is this number k n pk divided by 2n minus 1, because again I started with one stub, so I need to subtract one. Now I realize there is a small mistake in the sense that I probably should say it's probably also depend if I know something about x itself. But we take x at random, so I don't know anything about, no, we don't take it at random because we don't start with somebody of degree 0. So probably this is still a small approximation. Think about it. If this belongs to somebody of degree, if it is a vertex of degree k or not a vertex of degree k, it makes a difference. But okay, it's probably small. No, it would. We would have to consider two cases. Either is x is at a vertex of degree k or not at a vertex of degree k. Because if it is at a vertex of degree k, we should indeed subtract 1 on the numerator because there is one less stub which is available. Okay. But what is this number? I just continue the computation. This is equal to pk. I just factor the pk. Then we have k. And what is this n over 2m minus 1? It's like before. It is in fact k times 1 plus O of 1 over n. I just let you do the small computation, the link between, 2m divided by n is this k. And then we have also 1 over n. Okay. So it's exactly this. And probably the distinction between this one is also of degree k or not, is probably can be put in this factor. It doesn't really matter. But what you observe compared to the initial answer, it's indeed not the same. We have this factor, which is k dependent. The denominator, the notation is a little bit, remember, this is just a constant. I consider maybe it's better to write it like this, k over the expected degree times 1 plus k. And now, still in the same, what is the expected degree of y? Still in this framework, what is the expected degree of y? Then this is E, because now we have the distribution, we have the probability that it's has degree k. So the expectation is just a sum. So this is equal to the sum of k times this probability. So times, first I write this k n pk over 2n minus 1. This is the exact, but I can replace also by what we have here. And if you do the computation, it gives us, I'll let you do it, it's simple. It gives us k squared over k. And it's an approximation in the limit. I forget the term 1 over n. But observe that this is not equal to k. And k would have been your answer if we think that this is a distribution, we would have answered this, and then the expectation would have been exactly this k. But this number in general is not. Is it, which one is bigger? You can wonder which one is bigger. Is it the first one or the second one? So let's just compute the difference. The first one is bigger. Observe that. Wait, let me finish this argument. Observe that this k squared over k minus k, I want to compute this difference. This is 1 over k times k squared minus k squared. And you have probably seen this expression. So it makes 1 over k times the variance, which is usually denoted by sigma square, which is a variance, and it's bigger than 0. Variance of degree distribution. So it means they are not equal, but in general, they are bigger. And what does it mean? So remember the original framework. We have vertices with a certain number of stubs. They are connected in a certain way. Are connected in your set. I started with 1, my initial point, and this is x. I go to y. Suppose I go to y. Now this is. We have the expected degree of y is bigger. Be really careful. The expected degree of y is bigger than the expected degree on this graph, which is not surprising because in the expected degree of the entire graph, we have this guy, while in my computation, I don't see this one because I never reach it. But this has an impact on your daily life. Not maybe so much, but it's this idea, if you think about connections between people, you have an observation, and I put a table. The expected number of connections of your connections is bigger, or the number of friends of your friend is bigger than your number of friends. In easy words. Simply because if you are an arbitrary guy inside this picture, your expectation, the number of friends, is given by this, if you're arbitrary. But if you look at one of your friends, one of your friends, the expected number of friends this guy has is bigger. It is this number. Yeah, it's just a computation. There is nothing magic. It's just because, but I say we cheat a little bit because if you are this guy, you have no friend to do this experience. But okay, so if you start with X and make a connection with Y, then this Y has a bigger, the expected number of connections, so the expected degree is bigger than the expected degree on an arbitrary graph like this. Okay. Yes.
This sum should start from 1 because we consider, no, we don't consider 0.
Sorry?
The sum starts from k equals 1.
You can start it at 0 because if you multiply by 0, it doesn't change. Yeah, but yeah. There is a related concept. I'm not going to develop, but a related concept which is written in the note. It's what is called the excess degree, which play a certain role in some computation. I will not present it because there is one application I really want to do today. But yeah, it's half of a page about this excess degree. It's related to the degree of this Y again. And now, with this excess degree, you can do one computation. Again, it's given in the notes. I give you just the answer. You can compute remember the clustering coefficient, which I recall at the beginning. So we can compute the expectation of these clustering coefficients. And remember, very roughly, it is the number of closed triangles divided by the number of 3 points connected. I cannot give you the exact computation because I haven't introduced this excess degree, but it's just 2 lines. I give you the answer. It's 1 over n times a square. This factor appear very many times. I recall for GNP model, C was equal to P. So what does it mean? It means it's a certain factor which can be computed times 1 over n. So what we observe, this clustering coefficient for n big is again very small. So it means if you want to make a model with a clustering coefficient which is not so small, again, you cannot use this. And this is not so surprising because look, you connect this guy at randoms. Again, there is no notion of distance. And this is what is missing in all these models. The connection between people in this room and people in America is probably very small between you and people in America. While in such a graph, the location doesn't matter. So if you want to have a more realistic model with a clustering coefficient, which really cluster mean it plays precisely with enough information which is local, you cannot use such model. It's better to use some models on a grid like this, where every point is connected to a few neighbors, but it's not connected. There is only a few which are connected to another part of the grid. Again, here you have many locally, but the number of connections between such a point and such a point is quite rare. So you need a space structure. While these models, space doesn't play any role. And that's why the clustering coefficients are becoming so small, because you have essentially the same probability to be connected to your neighbor than to the guy here. So and there exists such model on grids like this. And there is a famous subject which is called the small world problem or the small world graph. You can Google this. Okay. But again, this can be computed. What else can be computed? You can also compute in this model the existence of a giant component. What is the probability of having a giant component? What is the structure of the small components? Everything can be computed. But I want to do one more application. First, do you have any question? I know it's fast, and I don't ask you to remember or to understand everything, but just know that this exists, and you can come back to this when necessary. About the community structure, 11.3, which is a community. What do we mean by community? Oh, maybe it's the same thing as here. You have a complicated graph made like this. You want to say that people in this part are more, and people in this part are tightly connected, while the number of connections between these two parts is rather small. How can we encode this idea that we have two communities? I mean, it's the same graph, but the guy here are tightly connected, the guy here are or the vertices here are tightly connected, and you have only a few connections between these two groups. And this is the notion of community structure. Of course, you can have more than two communities, and even the notion of community is not very precise, because, how do you define these communities? Inside this community, maybe you have even two groups. So how do you decide that it's only one community or you have two communities? It's not precise. But okay, how can we deal with this idea? So communities is part of a graph which is tightly connected, but this tightly is not very precise, but which is tightly connected compared to other parts. Of course, we had this notion of vertices which were connected completely to each other. But this is probably too strong. It doesn't mean that all these vertices are connected to each other. Still, you have more here than on average. So how can we deal with this idea? And for this, precisely the model I have introduced can play a role. Do you have any question about the idea, what I'm trying to say? But I cannot tell a precise definition of community, but I think it's understandable. The idea how to test this is quite simple. So consider a graph G with adjacency, adjacency matrix A, capital A. Remember, I call it Aij. This adjacency matrix tells you the vertex xi is connected to the vertex xj. So it gives you the precise information about the graph. And let U be, I should mention, I should come back to the notation. G is a set of vertices on a set of edges. So let U be inside U, inside the set of vertices. So I consider a subfamily of vertices. Then the number of edges in U is given by, in terms of the adjacency matrix, is given by, remember, it's a sum over I and j of Aij, but I and j inside U. Or maybe I should, okay, I should write xi and xj. Yeah, it's I, xj. No, I is a vertex, so I just call I and j inside U. I do a mistake. What is a mistake? I write this. I don't get the number of edges. I need to divide by 2, yes, because I count all of them twice, because it's a symmetric matrix. So indeed, this is correct. This is a number of edges inside the community given by U. Now, if we have a graph with our model, so this is, let's say, a realistic graph, or you find it in a certain example. So for the configuration model, this number is given by, and we can compute it, it's given by 1/2 sum ki kj over 2m g to U. Why? Because remember, this was a probability of having there was a -1, but I forget on purpose the -1. So the m is large, n is large, so I can forget the -1. This number was a probability of having one edge, and I do the sum over all I and j in U. And what is m? M in this case is the number of edges of the graph. Okay. So in a sense, we would like to compare these two quantities, because this is what happens in a certain model. I mean, let's say in reality, on your realistic situation. And this is what the number you would obtain if you consider the configuration model. And so we are going to study the difference 1/2 of sum I and j in U of Aij minus ki kj over 2. We are going to study this. Because are we interested in a big difference or a small difference? Are we what do you think? We want to have this big or small? If we are in a community, this should be big, because this is for a graph taken at random. So as I said, there is no idea of location, there is no space. While this, if I want to detect a community, this, by taking precisely in a U in one community, this should be larger, because this number, the first one should be larger than the second one, if we are in a community. If it's completely at random, it should essentially be 0. But if U is really a tightly connected path, this number should be bigger. Okay. observation, and it's going to play a role. If I do the sum over all I in V first, all I in V of Aij minus Ki Kj over 2n. What is this number? No. Somebody else. Or online, who can tell me what is this number? It's 0. Look, I sum over all. So the sum on I of this is the sum over I give me the number of connection at the vertex j. So it makes Kj. This is a property of the adjacency matrix. And if I sum over I just Ki, it gives me precisely 2m. So it makes minus 2m over 2m times Kj. It's 0. And now you understand why I had to forget this -1 on the denominator, otherwise it doesn't work. But if m is large, this is fine. And you can do the same. Now, please do the sum over j. You're also going to get 0, simply because it's symmetric. Okay. So this is an observation I need in a minute. But this is for the sum over the entire graph. Now, if I have two communities, if I suppose I have two communities with many connections here, and few connections. Okay, this is what I would like to have. I'm going to define Q. So here we have x1, x2. Here we have x3, x4. It depends. But I'm going to say that this is the community L1. This is the community L2. I just give a name, community. So I'm going to define Q. I have certain formula. For some reason, it doesn't play any role. For some reason, I divide by 2m. But this is not important. Sum over j and I and j of Aij minus Ki Kj divided by 2m. And I'm going to write a delta Li Lj. Okay, it's a little bit fast. I don't understand. What does it mean? It means I'm going to add the index L1 for all vertices in this set. And I'm going to write the information L2. Think about two colors. We have the yellow guy and the blue guy. And I need to say these points are yellow, these ones are blue. So I'm defining a certain quantity, which is, it's a definition, this factor, which doesn't matter. Again, I sum over everybody. But I take care of keeping in this sum, I sum this for the blue guy or the yellow one. So I need to have L, you know this Kronecker delta. It's 1 or 0. It's 1 if these two numbers are the same, it's 0 otherwise. So I sum this into the first community and I do the sum into the second community. I could write two sums, the sum over this one, the sum over this one, and it means I don't consider anything here. Okay. Yes.
This is assume you already know the community?
No, I'm trying to develop a way to find the communities. But before I can develop it, I need to introduce something. So for now, I don't know these two communities. my aim is indeed to find L1, L2. Okay. And I'm going to call this, I give a name, I call this Bij. Okay, this quantity. And now observation. It's a rather stupid but clever observation. Let me define L1 as 1. The blue guy, I call them 1. The L2, I give them the number -1. Okay. What is L1, L2 -1 or +1 over 2? Can you tell me what it is? This is nothing but delta L1, L2. Look, when both are the same, it makes 1. When both are different, it makes 0. So this is just one way to realize this delta L1, L2 with two numbers. Okay, I guess everybody agrees with this. So I'm going to replace this Kronecker delta with L1, L2 plus 1 divided by 2. Okay, so it's equal to 1 over 2m sum ij bij, I already introduced this, and then we have L1, L2 plus 1 divided by 2. Okay, and now I can simplify. Sum ij. Observe that I sum over everybody because the communities are taken, I take care of the communities by L1 and L2. And I'm claiming that this is the same as this, Lij. And we have a factor 2. Why can I forget the +1? Remember, it was here. The sum of Aij minus Kikj over 2, if I sum over I or if I sum over k, it's 0. This factor, I just have the sum either over I or over j, it's 0. So I can forget this term. I get this. But now, linear algebra. This is 1 over 4m L transpose B L. And what is this L? It is a huge vector. It's an element of C or no, so R. It's an element of Rn. Why? Because remember, for the first vertex, it's either 1 or -1. So in fact, I can be more precise. It's an element of -1, 1 power n, which is a vector in Rn. Because the first component is either 1 or -1, depending if x1 is here or here, x2, x3, and so on. Right? So this is a n times n matrix. And these two vectors are vectors in Rn, but in fact, they are 1 or -1 at each entry. No. Somebody has a question. Is it clear for everybody? I just rewrite it as a matrix applied to a vector, and taking the transpose, it makes a scalar product. Yes, but
in the framework we are working, we're not allowing multiple edges.
Does it?
Because if you said L1 to 1 or -1, that says only one edge between 2 points if there are.
No, I think multiple edges are allowed. There is no problem. There is no problem. Think again. Okay. Remember now my aim is to find communities, so to find L1 and L2. How I'm going to do it, I want extremum. I want to have extremum of Q because remember, my aim is to have tightly connected things. So among all possible two communities. I want to have one with big number here, right? If I take a different, two different communities, then I'm losing many edges between this part and this part, so this Q would be smaller, right? So I want to have an extremum of Q under a constraint. And what is the constraint? The constraint is that L, what is the norm of L, the Euclidean norm or the usual norm of L? Sorry? Yes, so it makes square root of n. You sum n times 1, but this gives you the norm square, so you need the square root. Okay, extremum of a function under a constraint. Who give you calculus 1? It should remind you something. Extremum under constraint, or maybe it's calculus 2. It's Lagrange, sorry, calculus 2. Someone, yeah, calculus 2, Lagrange multiplier. You have a problem with a constraint. And so what is Lagrange multiplier? I will just try to finish. Lagrange multiplier. And so it means we have to look for gradient of L transpose BL equal to lambda gradient of the constraint, which is norm of L square minus n. I can put the square, the same constraint. This is, and if you take the gradient, now we have to cheat. It's not cheating. I cannot do a Lagrange multiplier in this space because I cannot take derivative. That's why I have to consider that L is allowed to take integers, real values. Otherwise, this is not well defined. But if I define this Lagrange multiplier, I end up with the following problem. BL is equal to lambda L. Take the gradient, think about it. You obtain a factor 2 because you have two derivatives, but you also have a factor 2 when you differentiate here. What is this problem? Eigenvalue, eigenvector problem. So we are looking for, now which eigenvalue do we look for? We look for extremum of Q. We look for the biggest one. So we looking for largest eigenvalue of B, because we are looking for an extremum. It exists because B is symmetric. So they exist, maybe with some multiplicity, but they exist. However, now, what is the end of the game? So let's suppose we find the eigenvalue. Then what is the eigenvector? We are going to find eigenvector satisfying L is in Rn. Norm of L, I can fix it to square root of n, which is not what I want, because I would like to have only these guys. And for sure, I cannot get such, I mean, there is no chance. So then you need to do something. We fix, and I'm not claiming that this is the best solution, but it gives you fix L star J for the solution, which is 1 if Lj is bigger than equal to 0, minus 1 if Lj is smaller than 0. So you have this eigenvector. Each entry is a real number. And now I just take the sign of this entry. So in a sense, this is a ball in Rn, many dimensions. We have one eigenvector. And what I'm taking, I'm just looking if it, for each entry separately, I look if it is positive or negative. That's the only thing I can do. Maybe I can do better if I accept to have more communities, but I introduce only 2 communities. So you fix this, and it gives you at least it gives you one solution. This gives you two communities. 2 communities with large Q. As I said from the very beginning, there is not a unique definition, there is not a unique solution. So you cannot be sure that if you spend a long, long time, you cannot find something better, but it's a first solution. It's a first approximation. And it only involves things that you know. We have a problem with constraint. The thing is, we cannot stay in this -1 power n. We have to go to Rn. But then when we have the solution, so when we have the eigenvalue and the eigenvector, we just arrange to keep just the sign, which is better than nothing. So we have found one solution. There are probably better algorithms, but this is considered as a complicated problem. Having a big graph, how do you define communities? What is the definition? How many communities and how to find them? It's a hard problem. But this is one partial solution. Thank you. We have only one more lecture next week about epidemiology. I will put many things, propagation of epidemics.